Hey guys, this is Mr. Secoder. In this video, we are going to do a competitive programming problem which is related to bit manipulation. So the problem is, you are given an integer and let's say we need to count the number of set bits in that integer. So for example, let me take, we have an integer 6, let's say. So what is a binary representation of it? It's 1 1 0. So the number of set bits in this 6 is 2, that is these two. Okay, so let's take another example. So let's take the integer 8. So what is the binary representation of it? It's 1 0 0 0. It is a binary representation of it, the binary representation of 8. So the number of set bits is 1. So here we need the number of set bits is 1, and here the number of set bits is 2. So our solution need to print the number of set bits in an integer. Let's say for example it's a 32-bit integer. Okay, so but we can extend our solutions to long and other long integer as well. What I suggest is, so you pause this video now and think of how to solve this problem. I know it's easier, so because of which I even gone through different solutions. It's as we go through the solutions, I'll try to optimize it, and I'm sure you're going to learn something out of this problems. So without wasting your time, let's get into it. So our first approach, let's think of this. So what we do is, let's say we were given an integer which converts into a binary representation as 1 1 0 1 0, let's say. Okay, so what we're going to, let's say this is n. So what the simple solution would be, iterate through all each and every bit, and then check if that specific bit is set or not. So the easier way to do is just simply just compare the rightmost set bit, which is, and to check if this bit is set or not, what you can do is you can simply do a logical AND operation with 1. Okay, so if the last bit is set, then you'll get a result of 1. Since it is not set, you'll get a result of 0. Okay, so in order to check the second bit, what you can do is you can do a right shift operation on this. So if you do that, what happens is when you perform this right shift operation, so you will get 0 at front of this, right, at most significant bit, and this is moved one step ahead, 1 bit rightwards. So now the rightmost set bit, now you can check if the right bit, that is the least significant bit, is set or not by simply doing an AND operation with 1. So now in this case we'll get 1, because we are doing a logical AND operation between both of the ones. So whenever you have 1, then you can keep track of this in a count operation, and you can increment this count whenever you get an AND operation of 1. So similarly you can do it, you can again do a right shift operation which will give you 0 0 1 1 0, and then you can do an AND operation with 1 to check if the right bit is set or not, and if that's not it will become 0, it will be 0. If that is 1, then you'll get 1. Similarly you can do this operation till all the bits are 0, which is nothing but n is becoming 0. Okay, You'll understand. If you look at the code, then it will be clear for you. Let's look at the first solution of it, which is a simple solution. So this problem is taken from the Geeks for Geeks. I'll put a link in the description, or I'll put all the code and the link in my blog post, and I'll put that my blog post link in the description so that you can refer it. So he is expected to have a time complexity of log n. So since we are iterating through all the bits, the number of bits is approximated to the log n. So yeah, what you're going to do is, so we'll maintain a count, and we iterate till n is positive, and if the last bit is set, then we are incrementing. If the last bit is not set, then it will be 0. If the last bit is set, then this will be 1, which is nothing but, in case of last bit set, we are incrementing the count. If not, we are not doing anything. Okay, and then after this, at the end of the iteration, we are performing a right shift propagation, so that the next bit, the previous bit of the least significant bit will become the least significant bit in the next iteration. So we'll do it until the n is exhausted. The n is 0. So, and finally we are returning this count. So what is the time complexity of it? Since we are iterating through all the bits, the time complexity is, let's say, big O of k, where k is a number of bits in an integer. Can we optimize this? Yes, we can optimize this. So think, pause this video now and think how to optimize this. One hint is, try to make the algorithm such that it only iterates through the set bits. Let's get into it. So what we are going to do is, so before going to the actual solution, I would like to convey one thing. Let's listen to this statement carefully. When you are subtracting 1 from a decimal number, then it flips all the bits after the rightmost set bit, including the set bit itself of that specific number. Let me put into an example. Let's take an example of 10. What is the binary representation of it? It's 1 0 1 0, right? So what we do is, we will subtract like 10 minus 1, which is equal to 9, right? So let's write that binary representation of it, which is 1 0 0 1. What you can observe from this, so when you're subtracting from 1, from a decimal number, let's in this case 10, so whatever the bits till the rightmost set bit, what is the rightmost set bit? Here, this, right? So till that, all the bits are flipped. You can observe here, right? So 0 becomes 1 and 1 becomes 0. So let's take another example as well. Let's take the 9 itself. So what is 9 minus 1? 8, right? So what is the binary representation of 8? It's 1 0 0 0. So in this 9, what is the rightmost set bit? Which is 1, right? So what happens is, whatever the bits to the right of the rightmost set bit, including the right bit, is flipped. Here there is only one such bit, so which is 1, which is flipped to 0. Let's take another example. Let's even reduce from 7. Okay, 8 minus 1 is 7. What is its binary representation? It's 0 1 1 1. This example will clarify all your doubts. So if you're reducing 1, what is the rightmost set bit in 8? So this 1 is the rightmost set bit, right? So what happens is, including this rightmost set bit and to the right of this rightmost set bit, if you perform a minus 1 operation on 8, all these bits which are right to the rightmost set bit and the right bit and the rightmost set bit will be flipped. Here in this case, even if you have some 0, if you assume some 0 before, only the bit still this rightmost set bit and to the right of the rightmost set bit is flipped. So 1 becomes 0, 0 becomes 1, 0 becomes 1 and 0 becomes 1. I think this concept was clear, right? So now think of how we can use this trick to solve the actual problem, which is counting the number of set bits by iterating only through the set bits. I think you're done with your thinking process, so let's get into the our approach. So let's assume whatever the integer that we are given is n. So we know n minus 1, in n minus 1 it flips all the bits till the rightmost set bit. Okay, so if you consider this 10 and 9, okay, let's say the n is 10, n minus 1 is 9. So if we perform n and n minus 1, if we perform a logical operation between n and n minus 1, we know all these bits will become 0, right? So what I'm saying is the 10 is this and the n minus 1 is 1 0 0 1, right? So we already know that these bits are flipped version of above bits. So for sure this will become 0. What that mean? The rightmost set bit of the n is turned off. So what this n and logical and n minus 1 will do is it will turn off the rightmost set bit. So if you take this n 10, it will turn off the rightmost set bit, which is 1. If you take 1 0 1 0 1, then it will turn off the rightmost set bit, meaning it will give you the value of 1 0 1 0 0. Okay, so I think this logic is clear. So what our approach is, we will put this in a loop and we'll iterate till n becomes so in each iteration what you're going to do is we will set n to this value, n is equal to n and n minus 1. What it does, it will turn off the rightmost set bit. So we will again we'll put that value in a n and then we will again iterate. So in the next case it will let's say here in the first iteration it will turn off the rightmost set bit, which is 1 here, right? So in the next case what it's going to do is it will turn off this second rightmost which is rightmost set bit of the current position. Okay, so in the next loop what it's going to do, it's going to turn off this rightmost set bit as well. So in that case the value will become 0 0 0. Okay, so we'll do this until we reach it 0. So the number of times you iterate, as you can observe, the number of times you can iterate is a count of the set bits. So I think the idea is clear. Let's get into the solution, the code. So this is also known as brain Kernighan's algorithm. Okay, so what we are going to do is we are to keep track of the count, we declare a count variable. So till n is some positive integer, we increment this count, and for the next, and we are turning off the rightmost set bit and we are considering that as n. Okay, so you already know this logic, right? So and then the number of times we turn off this bit till n becomes 0 is nothing but the number of set bits count, right? So that's what we are counting here, and we are returning that value, so which is the number of set bits of the given integer. So what is the complexity of this? We are iterating only the number of times which is equal to the number of set bits of an integer. So obviously we try to optimize this, right? And is there any simple solution which you need not code much? Yes, there are inbuilt functions in GCC, so which you can leverage to get the count easily with a single line. So there is a function, a built-in underscore underscore built-in pop count. So what it's going to do is it's going to return the number of set bits in a integer that you pass. So what about long? So for the long, so now currently n is integer, right? This function will only accept integers. You can even pass L for there is another function which is similar to this, which is underscore underscore built-in underscore pop count L, which is for long, and pop count LL for long integer. I think you'll remember that. I think that idea is clear. So we will even go to another approach. There is another concept called bit set in C++ which you can use. So there is an inbuilt function for that bit set which counts the number of set bits in a given the bit set. So in C++, integer is having a size of 4 bytes, right? So each byte is 8, so 4 8s 32 bits. So we can declare a bit set of size 32, and we can pass the integer value here, and you can get the count of the number of set bits easily by using bitset.count. Okay, these two will be helpful in competitive programming because time matters, right? I think you learned something new out of this video, so don't forget to subscribe and don't forget to like. If you don't like this video, just comment, or even if you like this video and if you want to say some suggestions, or if you want to tell the different approach or anything, just comment in the comment section below, and don't forget to like, share and subscribe. Thank you. Stay safe.